Information can't be destroyed. That's one of the deepest rules in physics. Yet black holes seem to do exactly that: swallow information and erase it from the universe. If both statements are true, our current understanding of reality is inconsistent at a fundamental level. If one is false, entire pillars of modern physics collapse. This conflict is called the black hole information paradox, and it's not a side issue. It's a flashing red warning light on the dashboard of the universe, telling us that something, somewhere, in our best theories, is profoundly wrong. To understand the paradox, you need three ingredients: black holes, quantum mechanics, and information. Start with the black hole. Take enough mass, crush it into a small enough volume, and gravity wins absolutely. Around it forms an event horizon, a boundary where the escape velocity equals the speed of light. Cross that horizon, and no signal, no matter how energetic, can ever get back out. Classically, a black hole is simple. It's fully described by just three numbers: mass, electric charge, and spin. Everything else about what fell in, stars, planets, your favorite book, is gone. Now add quantum mechanics, which says the universe is made of information. The exact quantum state of every particle encodes what it is and how it can evolve. And crucially, quantum theory insists on unitarity. If you know the state now, you can, in principle, reconstruct the past and predict the future. No information is ever truly lost. Burn a book, and its words are scrambled into smoke, ash, and photons. But the information is still there in microscopic correlations. In a quantum universe, perfect shredders do not exist. So what happens when you throw that book into a black hole? Imagine you drop an asteroid into a black hole. Its detailed quantum state, the arrangement of every proton, neutron, and electron, carries an enormous amount of information. From far away, though, the black hole only changes in three ways. Its mass increases, its spin might shift, and its charge might change. This is the no-hair theorem. Black holes have no hair, no extra features to store all that detail. It's as if the universe takes a rich, complex story and replaces it with a single number on a scale. Classically, that's fine. But quantum mechanically, it looks like information has vanished behind the horizon, unreachable forever. For a while, physicists shrugged and said, fine, the information is still inside, hidden, but not destroyed. Then Stephen Hawking did something radical. In the 1970s, he combined quantum field theory with curved spacetime and discovered that black holes aren't perfectly black. Quantum fluctuations near the event horizon create pairs of particles. One falls in, the other escapes as radiation. Over incredibly long timescales, this Hawking radiation makes the black hole slowly evaporate. A solar mass black hole would take about 10 years to disappear. But when it finally vanishes, where did the information about everything it ate go? Hawking's original calculation said the radiation is purely thermal, like the glow from a hot coal. It depends only on the black hole's mass, charge, and spin, not on the details of what fell in. That means the outgoing radiation carries almost no information. If the black hole completely evaporates, the information about the initial quantum state is gone from the universe. This is not just hard to recover, it is fundamentally erased. That breaks unitarity. It says the universe can take a pure quantum state and turn it into a mixed random one. If that's true, quantum mechanics as we know it is incomplete. Why does this matter to you? Because unitarity isn't a minor technical detail. It underpins quantum computing, particle physics, and the way we interpret every experiment at the Large Hadron Collider. If information can be destroyed, then probabilities might not add up the way we think. Entanglement could behave differently. Even conservation of energy becomes subtle because information is tied to entropy, and entropy to thermodynamics. The information paradox is a stress test for any attempt to unify quantum mechanics with general relativity. Any theory of quantum gravity that survives must explain how black holes process, store, and release information without contradiction. Over decades, physicists have proposed escape routes. One idea: the information is encoded in subtle correlations within the Hawking radiation. At first, the radiation looks thermal, but after a page time, roughly when half the black hole's entropy has been radiated, the pattern changes and information starts to leak out. In this view, the final state of all the radiation is pure, not random. The math of holography and the ADAS-CFT correspondence strongly supports this. In certain toy universes, black holes do not destroy information. Instead, everything that falls in is somehow mirrored on a lower dimensional boundary, like a cosmic hard drive. But if information comes out, where is it stored while the black hole exists? One radical proposal is the firewall. To preserve unitarity and quantum entanglement rules, the event horizon might not be a gentle crossing at all. Instead, it could be a searing wall of high-energy quanta that destroys anything falling in, encoding its information in outgoing radiation. That saves information, but at the cost of breaking the equivalence principle, the idea that free fall feels like weightlessness, even at a horizon. Other ideas talk about soft hair on black holes, delicate quantum fields on the horizon that record what fell in, like a memory etched into space-time itself. More recently, tools called quantum extremal surfaces and island formulas have let theorists compute the entropy of Hawking radiation in simplified models. The result is striking. The entropy first rises, then falls, tracing the page curve expected if information is preserved. It's a huge hint that some version of unitarity survives in full quantum gravity. But these calculations live in idealized universes, not our messy, expanding cosmos. And they don't yet give a clear physical picture of what an astronaut would actually experience falling into a real black hole. Do they hit a firewall, glide through a smooth horizon, or encounter something stranger we don't have language for yet? So we're left with a profound question. When a black hole finally evaporates, does the universe remember everything it ever consumed, or does it forget? The answer will tell us whether space-time is fundamentally smooth or built from discrete quantum bits, whether gravity itself is an emergent phenomenon, and how deeply reality is woven together by entanglement. Somewhere, in the darkness, around those glowing rings in space, the universe is running an experiment we don't yet know how to read. Until we do, the information paradox remains a riddle at the heart of physics. And here at Terra Nova, we'll keep following it into the dark.